This is lecture number 4 in an introductory class in electricity and magnetism. And in this lecture, I'm going to describe the net electrostatic force and also a very special situation of the net electrostatic force called the Shell Theorem. So the learning outcomes of this lecture are to be able to calculate the net electrostatic force vector acting on a charge by a charge distribution. So this is a very mathematical and very vectory thing to do, and it's based on what you would have learned in the previous lecture video, lecture number 3. The second learning outcome is to use the results of the Shell theorem. That is not to perform the proof of the Shell theorem yourself, although that'd be really cool if you did get that under your belt. But the point of the lecture is to show you what the result of the Shell theorem is, and then for you to use the result of the Shell theorem to calculate electric forces. This is simply split up, so this lecture is split up into sort of 2 major portions that are definitely going to overlap, but I'm going to spend a lot of time at the beginning talking about what it means to calculate the net electrostatic force. It's going to start off discretely, that is, you may use a summation symbol, that capital sigma, but I'm also going to indicate that you can do the process of adding up the net electrostatic force in an infinitesimal way. So you're going to use an infinite sum of infinitesimal quantities, which are all of them vectors, and then you're going to do that continuous summation. That's called an integral. So let me put, this is vector integration. You're going to integrate vectors. I'll make an interesting comment that you may find some hesitancy with, or you might wonder about just in your own natural explorations of the topics. But I'm going to talk about whether or not you can block an electric charge's effect with other electric charges, or shadow it in a sense. So after this discussion, I'm going to talk about the Shell theorem. The Shell theorem is about spherical distributions of charge. So I'll mention more about this, but you know what a sphere is, right? Its cross-section is a circle. A sphere is it's an object that you can look at in 3 dimensions, but it really is just a 2-dimensional surface. Yeah, and I'm going to indicate that there is a Shell theorem that has 2 regions of efficacy. So I'll describe what that means. And I'll also comment on what's special about a conducting sphere and the Shell theorem versus an insulator sphere and the Shell theorem. And that is the lecture. So I'm going to move over and draw some pictures now. So the net electrostatic force, so let me write this out, electrostatic force. I might say that it comes with a symbol. Let's symbolize it as, say, F net, and we could put the designation electrostatic, but I'm only going to consider electrostatic interactions. So let me just call it F net. But I want to be really careful. It's on a particular charge. That is, I'm going to have to choose a charge to ask what is the net force acting upon the charge. And I indicated in the introduction to this video that you can start off thinking about, oops, I've misspelled discrete. It's discrete like this. So discrete in order to add up the net action or force on a charge, I can use a sigma, like a summation symbol. And it has an index, and maybe the index goes from 1 up to n or something like that. More on this in just a second. Or I can do what's referred to as the continuous case, and I will use an integral, right, for integration. So this integral, so if this is the summation over a bunch of particles indexed by n, this is an integration over where the charge is. This is the sum over all the charges, or the integration over all of the charge. In particular, for the Shell theorem, we're going to integrate over area. So this will be a two-dimensional type of integral. All right, but let's go back and let's study the discrete case. The discrete case is quite simple. Here's an example of a situation we could study. So here is a positive charge, another positive charge, a negative charge, and another negative charge, say. And I'm going to go and label these charges. So this is charge A, charge B, charge C, charge D. And for example, the charge of A will be called Q sub A. And let's imagine these are all point charges. So I have 4 point charges, all sort of close to each other. They can all interact with each other. And we're calling the amounts of charge QA, QB, QC, QD. QC and D are negative, and QA and B are positive. So if I want to know about, let's pick a charge at random. Let's concentrate on charge C. Let's ask, what is happening to charge number C? C is not for Coulomb. In this case, in this context, this is for a label on the charge. Okay, so what is happening to charge C? Well, charge C is attracted to B. It's repelled from D. And also, interestingly, so here's charge C. Check it out. I drew this on purpose. B is in between A and C. But what I mean by no blocking or shadows, what I mean by this is there is an attraction to A that's independent of the fact that B is in the way. So attracted to A, as if B did not exist. Right? This is what I mean by no blocking and no shadows. There's no way to hide the charge. Can't, so no hiding of charge. Okay, so this is kind of an important point. It kind of goes without saying. So what's happening to C? Here is one interaction. Here is a second interaction. And here is a third interaction. attracted to B. So B is quite close to C, right? They have some small distance compared to from A to C. Notice that I only care about what's happening to C. Yeah, so attracted to B, this is a force, it is a vector, it is on C by B, right? That's the first attraction force. Repelled from D, this one will be a force on C by D, right? It's on C in both cases because I only care about what's happening to C. And then down here, there is this third force. It's the force still on C because C is the only one that I care about for this particular problem. And it is by a charge A, which seems to be hidden by B, because if you imagine C looking out, C only sees B, but actually A still has an influence on C. So I've got 3 forces that all act on C. So this is what is happening to C in terms of force. And the net force, right, is something that I must ask, well, which object do you care about the net force for, right? So I care about what is the net force on C. It is simply the force on C by A plus the force on C by B plus the force on C by the only one left is D. So what I need to do is I need to add up these 3 force vectors. Each of these force vectors you can get if you had information about distances between A and C, A and B, A and D, but you also need to know something about the angle, right? Or maybe the coordinate locations of the charges, because really this is a vector summation. A and B's influence on C seem to be in the same direction. They're going to add easily. That's an easy one. But when I want to combine the forces by A and B on C to the force repelling C by D, right, that's going to need to be added as a vector, so we have to be more careful. Okay, so as an example, let's actually calculate the net force on a particular charge, but I'm going to kind of give myself an easy situation to solve. That is, hopefully a bunch of stuff will be obvious. So here we go. Let's imagine a coordinate system. Here's the x direction and the y direction. Remember, we're calling these j-hat movements, and these are i-hat direction movements. And let's, here's a simple one. Let's put a charge at the origin, and then a couple of charges. Let's do this. We'll put a charge here, here, and here. And I'm going to call this, so this is a rectangle here. Let's call this charge capital Q, and this charge Q1, Q2, and Q3. So Q1, Q2, and Q3 could be positive or negative charges. Yeah, it depends on what your homework problem might look like. Let's say that this distance right here is called W for width, and this distance is called H. So, so it's going to look like the force on Q by, for example, Q1, it's going to be 1 over 4 pi epsilon 0. So I'll just write this out. So acting on Q by Q1, it's going to be Q1 times capital Q with no absolute value bars, right? So we have to keep track of whether or not there is a minus sign or not. So no absolute value bars, divided by the distance from Q1 to Q squared, multiplied by the unit vector from Q1 to Q. So this is how we're going to calculate the force on capital Q by Q1. Then the force on capital Q by, for example, Q2, it looks exactly the same as what's up here, except for every time I see the index 1, I just put in a 2. So it'll be Q2 times capital Q divided by the distance from Q2 to capital Q squared times the unit vector from Q2 to capital Q. All right, and then the force on Q by the only other charge in the problem, Q3, is equal to 1 over 4 pi epsilon naught Q3 capital Q over the distance between Q3 and Q squared, and then multiplied by the unit vector Q3Q. There is a shorthand for this expression for the net force. Sorry to move the paper around. So the net force on capital Q is the sum from I equals 1 up to 3 of 1 over 4 pi epsilon naught. I'm going to pull a fast one. Hopefully you can keep up. I'm going to put capital Q. Capital Q is common everywhere. The only things that change are the value of the charge little q on top, because these Q1, Q2, Q3 aren't necessarily the same charges. Could be 1 microcoulomb minus 2 microcoulombs plus 3 microcoulombs, for example. Anyhow, so I'm going to take, but what is common is the 1 over 4 pi epsilon naught and the capital Q. So I'm going to put those common things together, put them together like this, and then multiply Q sub I divided by R sub Q sub I Q squared R hat Q sub I Q, like this. And so this is a sum of these terms. There happens to be 3 of those terms to add up the net force vector. But this factor here is common on all of it. So it can come out. It's common to all the terms. So it can come out and be in front. So I'm going to do that. You're allowed to do this. Just think about it mathematically. And it's times the result of doing the sum, I equals 1 up to 3 of Q sub I R hat Q sub I Q divided by R sub Q sub I Q squared. Right? Okay, so each of these terms in this problem are pretty easy to fill in. So it's 1 over 4 pi epsilon 0, capital Q, because that's common, right? So with number 1, here's number 1, the unit vector that points from charge 1 down to charge Q is negative j hat, and the distance squared is h squared. So this is Q1 times negative j hat divided by h squared. The next term has the same prefactor, like this. It's got a different charge to interact with. Q2 is over here. So this one, oops, I'm going to have to be sort of careful. I know how to write the distance squared, it's actually just the Pythagorean theorem distance, right? So the diagonal is w squared plus h squared. That's what the diagonal squared is. So w squared plus h squared is the answer to what the bottom is. I hope you can follow that. I skipped some steps to find that out, but I just simply used the Pythagorean theorem without the square root. But the upper thing, for lack of a better thing to write so far, I'm going to write q2 q hat, because I still need to figure this out. So let me put a red star. We're going to figure it out down here in just a second. But anyways, that's the answer to it, if I can write an expression for r hat q2 capital Q. So remember what r hat q2 to q is. It's equal to unit vector that points at q from q2, right? So here is q. You start at q2 and you have to look backwards in order to point at capital Q. That's what the meaning, right? That's the order of the indices. q2 is first and capital Q is second. This is easy. You just write the vector q2q and you divide by that vector's length. So not the length squared like what shows up here, but the length itself. Okay, so this vector that points from q2 back to q is really easy to write. It points backwards by w in the x direction, then backwards by h in the y direction. So this is minus w I hat minus h j hat, right? And then I divide by, so the length, not the length squared, but the length itself, is the square root of w squared plus h squared, right? So this thing right here is what needs to be placed there. And then you divide by another w squared plus h squared without a square root. Okay, and then this one is another easy one actually to write down, because it's strictly in the x direction. This was strictly in the y. This is a mixture of x and y, but the third one, q3, is strictly in the x direction. So this one is q3, and then w squared is the distance squared on the bottom, and the unit vector is minus I hat. So minus I hat is the unit vector that points back at capital Q from q3. So I've got expressions for each. These are all vectors, right? Sometimes if the little charge q sub I is negative, then you're going to gain a negative sign, and the stuff will just work out. You don't have to do anything by hand. This will all work out really nicely. You could just program this straight into a calculator or a computer, and it will always do the right thing for you without you having to make judgment calls on what SIGN to put in, what sign. Okay. This was discrete, right? So discrete means integer index. That's what that means. So we are adding together things that are individually vectors already that don't necessarily point in common directions. So when I add them up, I have to be very careful about the vector directions. All right. So that's an example of calculating the net electrostatic force by three charges acting on one. You could turn this around and ask, well, what's the net force on Q2 by Q3, capital Q, and Q1? And you will, in general, get a different answer, right? All right. So that's the discrete case, and the situation of no blocking. So what about continuous case. For a net electrostatic force. I'm going to just sort of allude to how it goes conceptually. All right. So here is a situation that is discrete still. So here is a capital Q, and over here is a whole bunch. Let's imagine a bunch of little charges, right? And they happen to look like they're along a line, but it doesn't really matter. Let's add charges. Right? So here is a charge distribution. And these are all point charges. And we might say that there are capital N of them. It sort of looks like I sprayed out maybe 30 point charges, individual point charges. So N point charges of charge Q sub I, where I is equal to a number like 1 up to capital N, right? And they can be positive or negative. They don't need to be the same charge. But the point is this is beginning to look like a little cloud of a bunch of point charges, right? And clouds seem to be similar to continuous, right? So, but it's still discrete because I can count them. It's a countable integer. And what's more, yeah, so it's a countable integer. And the process of discovering the net force, say, on Q, is just to do the sum of I equals 1 all the way up to N of the force on Q by charge Qi, right? Could be difficult. But simple idea, right? It's just a summation. Okay, so let's instead imagine that I have a really fine dusting, right? Such that it's really hard to distinguish the fact that there are individual charges. So this is more like a fine dust of small, and I want you to read infinitesimal, right? Point charges. And what's interesting here is I'm going to add up something that's going to be finite. It's going to be some number of newtons that's not infinite, and it's going to be most likely, right, in general, some number of newtons that's not strictly zero either. So in between 0 and infinite is called finite, even though 0 really is a finite value as well. And the way this sums up, though, is it's based on adding together a bunch of things that are not infinite, and nor are they necessarily in general 0 or close to 0. They're all finite, something that you can feel or is satisfying to write down as a number. If I go to a fine dust, infinitesimal point charges, these are very, very small, this is much more like a smear. And the idea is, in order to calculate the net force, I'm not going to resort to a sum over a discrete set of integer labels, I'm going to use a continuous integral that's going to have some sort of index or some sort of process to go over the charge smear and what it is adding up is really small contributions of force. So this is the net force acting on some charge Q. So let me put Q, I'm sort of crowding up. So here is Q, and each of these little charges is going to be considered a charge dq, a very small amount of charge. Can be positive, can be negative, and it's going to have units of coulombs, but it's a charge dq in the limit that dq is headed towards 0. It could be from the positive or the negative, though, in this case. So so the idea is the the force dF on Q by some dQ is really simply written down. It's just written down with Coulomb's law. It's 1 over 4 pi epsilon 0. The charge Q is there, but there is a charge dQ, and dQ is a distance r away, so you have to square that distance, and then you have to multiply by r hat that takes you from dq over to q. And this distance is between dq and q, the locations of the two different charges. And so you would take this expression for the small contribution to the net force on q by dq, and you would just simply take this expression, fill it in, and figure out how to come up with bounds. This step right here, this is where the physics is. The physics is just the physics of net force, honestly. But when you have this thing, you have to finish with math. You've got to figure out how to do this, right? And mathematicians tend to be really good at integrals, but it turns out that physics folks become really good at doing integrals, possibly better than mathematicians, although I'll let you have that argument. Yeah, so you make the physics decision on this is how I'm going to determine the net force, but I have this math problem to do, so you just walk over to the math department and ask somebody to help you. Okay, so that's the idea of the smeared out or continuous charge distribution. I'll shorten it to distro. Okay, so this continuous charge distro idea is where the Shell theorem comes from. This is how you would prove what's called the Shell theorem. So let me describe this to you. So the Shell theorem is in two parts. The parts are inside and outside. So let me describe what I mean by this. So consider a thin shell in the shape of a sphere, right? And what's more is this shell is coated in a perfectly uniform smear of charge. Whoops. Charge. So when we say perfectly uniform, what this means is the following. Here is this shell, and so it's a shape like a sphere. So here's, say, the equator of a sphere. And if I go and pick out any small sort of square on the shell of area, say, so this, I'm going to introduce the calculus idea of area dA, so it's always the same area. We always find the same charge dq. That is, if I make sure that I always pick a little square, always of area dA, I can go anywhere on the shell and discover that the same amount of charge is always located in the same area of patch. And the idea is it doesn't actually mean, it's not actually important that the area is actually a square. It just needs to be any area. So you can pick out a piece of patch that looks like this, and as long as this patch, this random other patch, has the same area, A and A, you are guaranteed for a perfectly uniform smear of charge that you will always find the same amount of charge Q in those patches, no matter where you check and what the shape is, as long as the areas are the same. Okay, that's what that means. If you have this case, this is called, and this is quite special, a spherically symmetric charge distribution. This is often, this is a very special case, and it's a very symmetric case. And symmetry just means pattern. It doesn't necessarily mean mirror symmetry, or things look similar in a mirror. It does not mean that. It means, it's more general. It just means that there is a spherical pattern to the charge distribution. And in particular, the pattern is the charge is always the same for the same amount of area. Okay, I'm beating that into the ground, kind of. So I've got this special charge distribution, and I told you that we are going to split between thinking inside the sphere and outside the sphere. So let's think inside first. So what this means is, if I have such a spherically symmetric charge distribution, so if I imagine going inside of the sphere, let me just put a little point. So this right here is a charge Q, and Q could be positive or negative. It could be a lot of charge or a little bit of charge. But the point is Q, let's say, is a distance r from the center of our sphere, when our sphere has radius capital R, where the radius of the sphere is bigger than the distance of the charge Q from the center of the sphere. So remember that this sphere out here has charge on it, that it's not related to the charge capital Q on the inside of the sphere. But I just have some point charge on the inside of the sphere, and the sphere is coated in a spherically symmetric way with charge itself. Positive or negative, it doesn't matter. Lots of charge or a little bit of charge, does not matter. So it turns out, if point charge Q is inside the symmetric shell, the net force on Q by the shell right? All of the charge of the shell, it's pretty cool. It adds up to 0. And it does not matter where Q is inside the shell. Does not matter. Okay, so that's what is the inside rule. It's the inside part of the Shell theorem. So let me describe the outside part of the Shell theorem. So here is outside. So outside means that I have a uniformly charged spherical shell, and I have the charge Q somewhere outside. So here is the charge Q. Its distance from the center is bigger than the radius of the sphere itself. And it turns out, so I'm going to say that the center of the sphere is a distance little r from the point charge over here. So, and I'm also going to say that the charge, the net charge of the shell is called capital Q, right? So there is a certain amount of charge spread uniformly over the sphere, and the total amount of that charge is called Q net of the shell. Outside, so that is for little r bigger than the radius of the sphere, the net force on Q by the shell is equal to a really simple expression. It's pretty extraordinary, and this is the result of using the shell. Well, yeah, so it's extraordinary. So you got to do the integral and all the blah, 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 but it just simply boils down to, after you do all the calculus, it's 1 over 4 pi epsilon naught, the charge Q, times the net charge of the shell, divided by the distance r squared, where r is simply the center-to-center distance between the spherical charge distribution and the point charge capital Q. Yeah, so it comes in an inside. The Shell theorem is an inside story where there is no net force, and an outside story where the net force makes it appear that this spherical shell is behaving as a point charge. So you'd say behaves as a point charge. Okay, so this is a simplification. And you can use, that is, you have to properly use the Shell theorem to avoid doing crazy integrals, right? So we have a tool. Consider the Shell theorem as a tool, but you have to use the tool properly. You have to know how to use it. Okay, so some things to note. Shell theorem does not work for charged conductors. And the reason is because of induced dipoles. So the idea is let's imagine Q, let's say it's a positive charge, and I have a conductor over here, and the charge Q is on the outside of the conductor. And let's say that the net charge of this conductor happens to be 0. There is no net charge. It's got the same number of pluses as minuses. But if this charge Q is a positive charge, it's going to attract negative charge over to the left side and leave over positive charge on the right-hand side, and this situation is not spherically symmetric, right? So this is an induced dipole. It's induced by the interaction between this external charge and the conduction electrons on the conductor. If I was to use the Shell theorem improperly, what I would say is, well, this is equal to 0, because here it is, right? And the net force on capital Q right here by this shell of no net charge, I would calculate it, right? If any factor in a bunch of factors is 0, then the result is 0. But clearly, this is attractive. That is, F on Q by the shell is not 0, right? So this is a failure of the Shell theorem, but it's a failure, not of the Shell theorem actually, it's a failure of a person improperly depending on the charge to remain spherically symmetric. Shell theorem works really well with insulators, because the charge on an insulator is not allowed to flow around in response to an external charge's influence. Okay, so that's the Shell theorem. Real quick example that ties together a few issues. I'm going to have 3 shells. With different radii, right? The shells are S1, S2, and S3, and the radiuses are R1, R2, and R3, for example. And each of these shells has net charges, right, of Q1, Q2, and Q3. And what I'm going to do is distribute the shells in an interesting way. So here is an x-axis, say, and one of the shells is centered on the x-axis. Another shell is centered on the x-axis somewhere else. And then there is a third shell that's centered, say, here, and it actually can consume the other 2 shells. It's just on the outside. So you've got 2 shells that are on the inside of a third really large shell. And I'm going to put a charge capital Q way over here. Let's call this is S number 1, S number 2, and S number 3. The distance that Q is from S1, let's call this R1. Q is R3 from the center of S3, and Q is, you guessed it, R2 from the center of S2. All right, so it definitely looks like R1 is bigger than the radius of shell 1, right? That just indicates that Q is outside S1. R3 is smaller than the radius of the shell R3, so Q is inside S3, and R2 is bigger than, so here's R2, it's the distance between Q and the center of the shell S2. It is bigger than the radius of the shell S2, so that means that our interesting little point charge Q is outside S2. And so if I want to know what is the net force acting on Q by the 3 shells, it's the sum of the forces by the individual shells. So it's the force on Q by shell number 1 plus the force on Q by shell number 2 plus the force on Q by shell number 3. But there's a really quick thing we can say. We can use the inside rule, and the force on our charge capital Q by the shell S3 is 0, but the other two are not 0. So I'll have to figure this out, and I'll have to figure this out, but because they are uniform shells of charge, right, spherically symmetric uniform shells of charge, they each have different charge density or charge distributions or net charges, and these two just amount to doing the to treating the shells like point charges is the idea. Notice that even though S1 sort of blocks S2, right? There is no blocking of force. So I do have to include them, right? So the force on Q by S1, and then it kind of looks like maybe S2 might be blocked by S1, and this might be 0 on capital Q, but that's not true. You have to include it as if S1 didn't exist. Yeah. Okay, so that's an example of using the Shell theorem to begin to solve a problem.